Hi, my name is Tom Heffel, and this channel is all about helping students learn chemistry. We're going to continue our video series on equilibrium problems. This is going to be problem number 2, and these problems will get progressively more challenging. Okay, so this is kind of like at the beginning. Okay, so we're only at problem 2. So if we're looking at question number 2, okay, right here is the prompt number 2. Okay, so if you want to pause the video and copy this, okay, and then you maybe even try to solve it on your own. Okay, and then when you come back, okay, we'll be working on this problem. Okay, so this problem states that we got 22 molarity of A. So we don't have to calculate the molarity in this problem. Okay, it's just coming out right out and telling us, hey, the molarity of A is 22, which is really high. The molarity of B is going to be 38. It doesn't tell us anything about C or D in the prompt, okay? But it does tell us when equilibrium is established, the concentration of D is going to be 5. Okay, so at equilibrium for D, the molarity is going to be 5. So everything that's in a square up here are the givens in the prompt, and then the question's asking, what is K sub C equal to? Okay, and we need to figure this out, okay, using an ice chart again. So the first thing that I notice is that this starts out with no D and it jumps up to 5D. So I know that the change in D is going to be 5 molarity. And as soon as I know the change of one of them, I can figure out the change of all of them using my stoichiometry skills, okay? So what I'm going to do is I'm going to do some mole-to-mole conversions to convert D into C, into B, into A to figure out all their changes, okay? So I'm always using this as my given, though. So I'm going to start out over here. We're going to say if we have 5 moles per liter of D, okay, moles per liter, which is molarity of D, and I wanted to change that to C, all I would have to do is this mole conversion from moles of D to moles of C, and that's a 6:2 ratio. 6 for the D, and then 2 for the C. So 5 times 2 divided by 6 is going to be 1.67. So I know that the C increased by 1.67 because of this 6:2 mole ratio is 5 to 1.67. And then I just do the same thing, okay, but I switch the chemical to B and to A with this given, okay? Now, I will tell you, a lot of chemistry people will end up not writing this as moles per liter, but they'll do it as this, molarity of D, and they'll go molarity of D to molarity of C and do that 2:6 ratio. And this just looks a little bit cleaner. Now, this is technically like the mole-to-mole conversion, okay? But as long as the volume doesn't change, you can do it this way as well. So whatever you're most comfortable with is the way that I would recommend doing it, okay? Now, the next part, I'm going to not go to C, but I want to go to B and A. So I'm going to go to molarity of C this time, and the ratio between I'm going to go to B this time. Sorry. So the ratio between D and B is a 6:3 ratio. So 6 for the D, but 3 for the B. So 5 times 3 is 15 divided by 6. Okay, that's going to the change is going to be 2.50, right? So 5 times 3 is 15 divided by 6, okay, is going to give you 2.5, right? So one thing I want to talk about here is that this number is no longer positive because it's a reactant. Okay, this is going to go down because as this goes down, as the reactants are consumed, the products are produced. And I know this is going to shift to the right initially because there's no products. Okay, so these things are going to be made, but these things are going to be consumed. Okay. And then lastly, I'm just going to take that 5 molarity of D one last time, and I'm going to go from molarity of D to molarity of A, and that ratio is 6:5, okay? 6 for the D and 5 for the A, so 5 times 5 is 25 divided by 6 means that this is going to go down 4.17, okay? And that's how that math works. So I use this to calculate this, this, and this using these train tracks, okay? Now, I'm going to figure out the equilibrium position by taking the initial amounts, okay, and adjusting them by the change. So 22 minus 4.17 gives me 17.83 molarity. 38 minus 2.5 gives me 35.5 molarity. And 0 plus 1.67 gives me 1.67 molarity. Now, I'm going to use that information to calculate my K sub C. Now, remember, K sub C, you have to use the equilibrium expression, which is the products over the reactants. So let's go ahead and set up the expression first and then plug our numbers in. Okay, so products over the reactants where the coefficients are the exponents. So we got 5 and 3 on A and B, 5 and 3 on A and B, and 2 and 6 on C and D. Okay, so 2 and 6 on the C and D. This is the equilibrium expression, okay? And what we're going to do is we're going to plug these numbers in. 1.67 and 5 for C and D. So 1.67 and 5 for C and D, and that's 2 to the 6 and the 6, sorry. And then A and B is 17.83, 17.83 to the 5th, and the B is 35.5 to the 3rd power. Now, I don't think I'm going to be able to cross things out this time, just using logic. I'm probably going to have to use a calculator to do all this math, okay? And when you plug everything into your calculator, you should get this answer of 5.4 times 10 to the negative 7, okay? Now, this value is a really small number, okay? Which tells you if it's a small number, okay, it must mean that the denominator is really, really large. And if the denominator is really large, it looks like it's going to favor the reactant side. And if you look at all these molarities, the molarities of the reactants is much larger than the molarity of the products. And that's what yields us such a small K sub C value, okay, which tells us this is going to favor the reactant side versus the product side. If you found this content helpful, please give it a like and subscribe. We're going to continue this video series with a problem that's a little bit more challenging than this one.